In this video, we're going to start talking about regression and residuals. When you have a group of data that represents a linear or near linear relationship, you can draw something called a regression line. You may have heard of a linear regression or a line of best fit. This is essentially the same thing. In statistics speak, a regression line is a line that describes how a response variable y, so your output, how that changes as an explanatory variable x, your input, changes. So one way to express a regression line or a line of best fit is in this form. So we have a y hat, yes, that is a little hat that the y is wearing, it's precious, is equal to b naught plus b1 times x. So before you get all wrapped up in those variables, a line of best fit is a line at the end of the day. That's your y equals mx plus b, where the number b1 here is our m, it's our slope that's attached to the x, and then b naught is our y-intercept. Now obviously, depending on the data, those numbers have different meanings, but we know that. It's statistics after all. Using an example, which is what we love to do, we have some information about used Ford F-150s with the input x, so our explanatory variable is miles driven, so the number of miles, that correspond to our response variable y, which is the price. So if we were to graph a scatter plot of all of this data with all these little red dots here, where miles driven is on the x-axis and its price is on the y-axis, we could calculate, we could find that y hat, we could find that line of best fit, that regression line that would make a pretty good prediction as to what the cost of a used Ford F-150 would be based on the number of miles driven. One thing you can do with a regression line or a line of best fit is to make predictions, because, you know, we love to make predictions when we gather data. That's one reason why we do it. So let's see what. So for example, what if we wanted to predict the price of a used Ford F-150 that has roughly 100,000 miles on it? What I would do is I would take my regression line formula and I would substitute 100,000 miles for x, because that's our x variable, and I would get this rough estimate of a price, which is almost $22,000. Now, if I wanted to take that a step further and say, all right, let's go above and beyond the data that's been collected, I'm curious what this regression line would give me for 300,000 miles. Now, that wasn't a data point or anywhere near any of the data points that we had for the number of miles. It looks like we didn't even get to 160,000 miles. So let's see, all right, could this predict something beyond the scope of our inputs? And when I calculate that, when I put in 300,000 miles into this formula for price, it gives me a negative price. Now, that doesn't mean that the truck will be free or that they will pay you to take the truck off their hands. Now, I don't know. You could maybe find that. That might be realistic. But this regression line doesn't quite work with something that is out of the scope of the data that we've collected. We would call that extrapolation. So extrapolation is the use of a regression line for prediction far outside the interval of x values, like 300k miles. That is over double what we put in to obtain the line. Such predictions are often not accurate. Yeah. So just beware, don't make predictions using values of x that are much larger or much smaller than those that actually appear in your data. So now let's talk about interpreting a regression line and what each of those things actually mean in terms of the context or the variables that we have. So like we said before, that b naught is our y-intercept. That's going to be our predicted value of y, or our output, when our x, or our input value, is 0. And then, of course, our slope, that number in front of the x, that's the amount by which the predicted value of y, or our output, changes when x increases by 1 unit, right? Because slope is rise over run, or the change in y over the change in x. So if it's just a number or a decimal, that's going to be over 1. If you have a fraction, obviously the denominator, if it's not 1, is going to change that value. But, I digress. All right, let's look at an example. So that's the scatter plot and the regression line for those used F-150s where we've got miles driven and we've got their price. All right, Y is price, X is miles driven. So our y-intercept, this B naught value, is 38,257. That is the predicted price of that used Ford F-150 that's been driven 0 miles. I've never seen one sold like that, but hey, maybe you have. And then the value of our slope in terms of the actual data is the predicted price of a used Ford F-150. That goes down by about 16 cents for each additional mile it's been driven. So that's what the slope means in this context. Now, I hate to break it to you, but regression lines of best fit, they're not perfect. Not when we use real world data. So we know that lines of best fit are not going to pass through every single data point, creating a seamless line that, hits every single point. It just doesn't happen. So there's going to be some distances between your points and the line of best fit or your regression line. We call those residuals. So, for example, we have this regression line for our used Ford F-150s with their miles driven and their corresponding price. Now, we drew a line of best fit. We got as close as we could that would model through all those data points. Now, there's going to be vertical distance because we are using that line to predict Y from X. All of these black lines here represent the residuals of your actual data point to the line of best fit. So that's what a residual is. Your actual Y value subtracted your predicted Y value, or your little Y hat. So let's actually find the residual amount for one data point. Let's actually take the first data point that we have, which is a Ford F-150 that was driven 70,583 miles, and it cost $21,994. What a deal? I don't know. So if we wanted to find the price, so on that blue line here, if we wanted to predict what another Ford F-150 could cost, we'd take our regression line formula and we'd plug in 70,583 miles into that, and we would get the predicted cost. Now, again, this is the blue line cost, which is $26,759. Now, we happen to know that that is over the amount that someone actually paid, or the cost of the actual vehicle at 70 plus thousand miles. So in order to find the residual, we take the actual Y, so that is the actual cost here, 21,994, and we subtract the predicted cost from our residual line, and we find that it is negative $4,765. So that means, in terms of context, as far as our residual goes, the actual price of the truck is $4,765 less than the cost predicted. Now let's work through an example calculating and interpreting residuals that has nothing to do with used Ford F-150s. This one's called, Can You Grab More Than Expected? So there was a candy grab activity in Mr. Tyson's class where they measured the hand span in centimeters and the number of starbursts that hand could grab in one grab. So we've got our data points in this scatter plot. We have our regression line here, and our job is to find and interpret the residual for Andre, who had a hand span of 22 centimeters and grabbed 36 Starburst candies. All right, so what we're essentially doing is we are finding the distance from this dot, which is the data point for our friend Andre here, and we want to know the distance from that dot to the line, which is essentially the residual value. So we need to take the actual Y, which we know is 36 Starburst candies, and we're going to subtract our predicted Y, which we're actually going to plug 22 into here and figure it out. So we find our Y hat to be 32.46, so our residual is the actual, so that's 36 minus our predicted, and that actually gives us 3.54 starburst. So that tells us that Andre grabbed 3.54 more starburst than predicted. So you may have figured out by now that we love a small residual when it comes to regression lines. We don't want a lot of difference between our predicted value and our actual values because we like to make good predictions. So something that you may have started to think about is, I wonder if we added up the residual values. So a good regression line has residual values that all add up, all of them. 0 residuals to positive and negative residuals, you add them all up, you get a sum of 0. Now that makes a good regression line. But what we actually prefer in statistics and what you're actually given when you find a regression line, whether you're using your calculator or another statistical piece of software, that regression line is actually what we call a least squares regression line. So you take all those residuals, you square them, and then you add them up. So while the sum of residuals being small or near 0 or 0 itself is great, what we're actually looking for is a minimized value of those sum of squared residuals. So you don't necessarily have to worry about this, but I do want you to know that the least squares regression line is the actual equation you get from your calculator. Now, let me show you how to do that on your calculator. So if you remember how to find a linear regression on your calculator, then you're in luck because it's the same process. So if you were to add that Ford F-150 data into your calculator, where miles driven is your L1 list, or whatever the first list is, your X list, and then your L2 list or your Y list is going to be the price, and you enter that in, you hit stat, you go over to the calc menu, you hit linreg, the A plus BX one, which should be the first one that shows up, and make sure you have your diagnostic on, so it gives you your R squared and your R values, which we will use in our next video. And that will give you your A and your B values here. So that's going to be the y-intercept there, and then that's going to give us our slope, which is actually the regression line that we've been using this entire video. And if you want to physically see how well that equation of our regression line or line of best fits your data points in your calculator, of course, you make sure your stat plot is on and you store that regression equation, depending on how your calculator likes to do that. If you do that, or you can type it in yourself, that's up to you. But if you store it or you type it in, here you go. Here's our scatter plot and our line of best fit, which looks very similar to the one that our textbook has used. Fancy that! All right, that's going to do it for this video. I'm going to skate on out of here. Just kidding, I can't roller skate. Thanks for watching.